Hello. Today we're going to talk about linear regression. Okay, so how to tell if two things are related or not. Okay, so here we're going to test the distance and ticket price of airfare, all right, using our summary statistics. Okay, so what does all that mean? First, you have to get your data. So to the city, the distance there, airfare, Boston airfare, right? So all your points are related to these things. So then here, let's get out our calculator. All right, you want to go to Stat, then click 1 for Edit, and then you want to input your data. So I put distance into list 1, and then into list 2, I put the fare. Now if there's already data and you want to get rid of it, just go up to the top. So highlight the top part, hit Clear, and then hit Enter. Okay. So get all your data points in there and double check to make sure all your data is in there correctly, okay? All right, because it's easy to, misplace a decimal or, reverse a digit or whatever. Okay, so to get our summary statistics, so our mean and our standard deviation, all right, what we want to do is we can do second stat. Nope, I lied, just stat. Sorry, stat, hit calc. I do that every time. All right, so go to one variable stat, so number 1. We want to do it on list 1, so just distance. Hit enter. We're not doing frequencies here. Okay. So our mean is 853.7. So that X with the line on top, it stands for your mean. So notice that's correct here. The standard deviation comes from the SX, okay? So SX is your standard deviation. So notice we have that here. And then you can do your, stat, calc, do variable stats for now list 2. To type list 2, you would press the second button. And then on mine, it's number 2. You see on the left, above the left-hand side of the button, there's an L2. You want to select that. Then hit enter. And then now we can see that, okay, our mean is correct and our standard deviation is the same. Okay, so we've got those numbers. Now we want to get our correlation. Okay, so to get that number, you want to go to stat. Well, I'm sorry, first, let's look at our scatter plot. So to view our scatter plot, you're going to press second Y equals. Second Y equals gets you to stat plots. Hit enter, turn it on, select the first one, which is scatter plots. We're going to make distance on list 1, and the fare depends on the distance, right? So list 2 is my Y. And then the mark is just how it's represented on your graph, okay? And then I'm going to clear out, okay, I do have a line, so I'm going to erase that and do zoom stat. If you do zoom stat, it's going to zoom in on your scatter plot, okay? So you can see we have the same scatter plot, so that looks good. Since it looks linear, okay, I can continue on. If this does not look linear, okay, it doesn't matter if it's a negative line, positive line, whatever, it just needs to be a line, okay? If your data does not look like a line, then either get new data or come see me. I think we can scale it and see if that'll help. Okay. All right, so, let's do linear. Okay, that's going to make life easier. All right, so now we want to get how related is the data is kind of what correlation does. So to get correlation, let's see, I'm going to go to my home screen, and then let's see, is it stat? Yes, so stat, calc, and then down here to number 8. Don't do number 4, do linear regression for A plus BX. All right, our X needs to be list 1. Y needs to be list 2, no frequency, calculate. and then there's going to give me my R value. So R is 0.694, okay, which is what I've got here. All right, so now how we're going to have to do it by hand, right? Show our math, you know, because we want to show how the calculator got it. We don't want to just, you know, spit that out, okay? All right, let's do this. So let's see. First, we need to find R squared. So it's R and R squared is very similar to standard deviation and your mean. Well, no, I'm sorry, your variance. What am I saying? Your variance is what we use for calculations, but standard deviation is what we talk about, okay? R is what we use for calculations. R squared makes more sense to describe. So R squared is literally, we just take our R value and we square it. And then we turn it into a percentage. So R squared is written as a percentage, okay, 48.2. And what R squared means in this context, okay, it's kind of like how, well, how strong your model is, okay? R squared is how related your data is. So in this case, 48.2% of the variability in airfare is accounted for by differences in distances traveled. So the other 50 some odd percent is accounted for other things. Maybe, you know, depends on how much they have to pay for employees, insurance prices, upkeep of the airfare, like maybe, or the airplanes, maybe that affects the airfare, okay? But 48% of that variation in airfare is affected or is caused by that distance traveled, okay? We can also use R squared to describe how strong a data set is, okay? So how strong is the model? So we would say basically the same thing, but that's what you're answering. So R squared is describing how strong the model is, okay? Hopefully that makes sense. Okay, so we are doing linear regression, right? We're trying to put our data on a line and predict it, right? So here we would like to start with our slope, right? We need a line, so need a slope. So to find the slope of the regression line, all we would need to do, oh, sorry, I didn't show you the formula. Okay, so the answer is in red. So the formula for getting that would be, sorry, I thought I had written this in here. So R times the standard deviation of Y over the standard deviation of X. Okay, so that is your slope. So we took our R value, standard deviation of Y over the standard deviation of X, because, right, rise over run. Okay, then we can do, or what the slope means in the context. Okay, so slope is your rise over run. So think about what we have here. We have distance, and then we have airfare. So your slope, think about it, is your rise over run. So in this case, we can describe the slope this way. All right, so every mile in distance, we expect the airfare to increase by 0.079, right? But that sounds very silly, right? We don't want to talk about 8 cents, okay, for every mile we fly. When we fly, we don't debate whether I'm going to fly to north of Tallahassee or south of Tallahassee, right? You're going to say Tallahassee or Jacksonville, okay? So you can adjust the slope when you're describing it. So here we can just multiply them both by 100. 100 miles for $7.90. Okay, that's more reasonable. Okay, but that's how you can describe what the slope is. All right, we also need the Y-intercept of our line. Okay, regression line, our line of best fit, our linear regression, that's all that line that we want. So to find the y-intercept, oh, and I didn't write the formula again, excuse me. Okay, so your y-intercept would just be your mean of the y's minus your slope, okay, times the mean of your x's. Okay, that's going to get you your y-intercept. Okay, so again, this is your mean of y data, x with a hat, not with a hat, that's something different. X with a bar is your mean of x data, and your m is your slope you just found. Okay, so that's 177. So what does that mean in this context, in this word problem? All right, so that's a base airfare. So that's $177. So this is like your fixed cost. So if I didn't, just to get on the plane, it's going to cost me $177. Okay, so with a zero distance, okay, the y-intercept would be zero distance, 0 for the x, so that's the y. Okay, sometimes the y-intercept doesn't make sense to your data. You know, if you're doing height and weight, it wouldn't make sense to have, you know, 0 height or 0 weight. Okay? Okay, so now we can write the equation of the linear model and put it all together. Okay, so in this case, this was our y-intercept. This was our slope. And this is what we plug in, okay? And this bar means predicted value. Oop. I hope I can write. Okay. Predicted value. So your y is going to have a hat on it. All right? Y means predicted. So make sure you get that. Okay, that hat. All right. So is it appropriate? All right, well, hold on. There's a couple things we need to do first. We can continue to back up our data showing residuals. So let me talk about what those are. All right, so first you estimate the fare. So use your new equation and plot it for 2 random data sets. Okay, so for 200 miles, plug it in, you get that. So we graph that, and then we plug in 2,000, and we graph that. So just so we're clear, this was the green point, and this was your pink point. Okay, so we went 2,000 miles and paid $334. Then we can graph our line. Okay, if you're doing it by hand, that's how I do it. Okay, so now we have our line on top of our scatter plot. Okay, so now we need to plot the residuals. Okay, so let's talk about how to find it. Well, if I travel 1,719 miles, it's $212. The residual is going to be has to do with your predicted value. So first find the predicted value, okay? And then, so if I had used just my equation, I would have predicted it cost me $312, okay? So the residual is what it actually was minus the predicted. Okay, so let me write that down. So the residual is the actual data set, or the actual y, minus the predicted. So the one you observed minus predicted. Now in this case, okay, I predicted way higher. That's why my residual was negative. Okay, you can have a negative or positive residual. So in this case, a positive residual is when the opposite would happen. My observed would be more than my predicted. Okay, so that the prediction was lower than the airfare. Okay, negative is the opposite. Okay, sometimes people flip these up all the time. Really think about it. Okay, look at it's observed minus the predicted. Okay, so now that we know how to get the residuals, let's plot them, all right, and make sure we get this graph because it's important that our residuals, right, are very small. We want them to be kind of all over the place too, all right? But first, let me show you how to do this with your calculator. Wait, hold on. Let me go back to the page that had my equation. Okay, so back to here. So if we were to graph it, okay, to get your line on your graph, go back to Stat Calc Linear Regressions number 8, list 1, list 2, and let's also store this equation as our first line. So let's do alpha trace y1 calculate. Okay, so then hopefully, okay, so see our A value and our B value were really good estimates too. Okay, just how the calculator did it, right? Exactly the same. So then here we've got our equation. So then we can look at the graph. So go to zoom 9, and here you'll see your equation through that. Okay, so it should be a good representation. So now it kind of verifies it. That looks good. And then now let's look at our residuals. So go back to your list. Go to Stat, Edit, List 3. Oh, yeah, I already put it there. Here, so let me clear that list and show you how I did it. Okay, so you're going to go to go to the top of the list, then go second Stat, and do number 7. And then it's going to do the residuals, everything there. And then let's see, we can change our graph. So let's just turn, let's turn this one on. I'll turn my second one on. And the first, we keep the X list as list 1, but now list 3 is my residuals. And so now when I do zoom stat, now I can get my residuals. Oh, and I didn't turn off the other ones. So if I turned off the other ones, I would have gotten just this. Okay, and so now that looks good. So our residuals are kind of scattered. There's no pattern to them. I have low ones here, high there. They're kind of all over the place. So being that's true, all right, that means a linear regression is a good model. All right, so that's when you can decide whether or not your data is good. So here, since the scatter plot is straight enough, the scatter plot looks linear, and the residuals plot shows no pattern, we can predict the airfare from distance flown. Okay, we can also tell because of our R squared is pretty reasonable in this. Okay, 48.2%. That's a pretty good indicator of the airfare change, or the change in airfare. But really, correlation really depends on what your data is looking at. There's some statistics out there where it needs 99.9% correlation. Okay, like if you don't have that, then your data is useless. Okay, so some data needs super perfect, almost practically spot on linear, but sometimes you don't need that much. Okay, it really just depends on your data, and that's kind of like a best guess. Okay, so really use your best judgment and kind of go from there. Right, but that's how you would describe your data. Okay, so hopefully this makes sense. If you've got any questions, feel free to ask me in class.